In commercial load calculations, the neutral is sized for the unbalanced portion of the load. This is because the neutral current is only generated by the unbalanced portion of the load. The National Electrical Code, or NEC, requires the neutral conductor to be sized for 100% of the unbalanced load, plus an additional allowance for future growth. This means the neutral conductor must be sized for 120% of the unbalanced load. The continuous load calculation is based on the total load, which includes both balanced and unbalanced portions. The balanced portion does not generate neutral current, and thus it is not factored into the neutral calculation. The neutral conductor is therefore sized for 100% of the unbalanced load, even though the continuous load calculation utilizes 125% of the total load. This sizing method aligns with NEC requirements, which mandate the neutral conductor size accommodate the unbalanced load, plus a margin for future growth. Here is an example to illustrate the difference. Imagine a total load of 100 amps. Within that, you have a balanced load of 80 amps and an unbalanced load of 20 amps. The neutral load is 100% of the unbalanced load, which is 20 amps. The neutral conductor size is 120% of the unbalanced load, equating to 24 amps. In this scenario, the neutral conductor is sized for 24 amps despite the continuous load calculation using 125% of the total load, or 100 amps. This is because the neutral current originates only from the unbalanced portion of the load, which is the 20 amps. Let's delve into the concepts of balanced and unbalanced loads to understand this better. In a balanced three-phase system, the currents in each of the three phases are equal in magnitude and are 120 degrees apart from each other. In a perfectly balanced system, the neutral current is zero. However, in real-world scenarios, loads are rarely perfectly balanced. This imbalance in the loads is what causes current to flow in the neutral conductor. The NEC provides guidelines for calculating the neutral load based on the type of loads connected. For example, for household ranges and dryers, a demand factor is permitted to be applied to the neutral load calculation, recognizing that these appliances do not typically operate at their full rated load continuously. Similarly, for fluorescent lighting, the NEC requires that the neutral conductor be sized to carry the maximum unbalanced load, taking into account the harmonic currents produced by these types of loads. Harmonic currents are multiples of the fundamental frequency, which is typically 60 Hz in the United States. These harmonic currents can cause overheating of the neutral conductor if it is not sized properly. The third harmonic is particularly problematic, as it is additive in the neutral conductor in a three-phase system. This means that the third harmonic currents from each of the three phases add together in the neutral conductor, potentially exceeding the capacity of the conductor if it is not sized correctly. To address this issue, the NEC requires that the neutral conductor be sized at 200% of the phase conductors for systems with significant nonlinear loads, such as those with a high proportion of fluorescent lighting or other electronic equipment. In addition to the harmonic considerations, the NEC also provides guidance on sizing the neutral conductor for voltage drop. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. To minimize voltage drop, the NEC recommends that the neutral conductor be sized to limit the voltage drop to no more than 3% of the source voltage. This may require increasing the size of the neutral conductor beyond what is required for ampacity considerations alone. The NEC also addresses the issue of neutral grounding. Grounding the neutral conductor is essential for safety, as it provides a low impedance path for fault current to flow back to the source. This allows the overcurrent protective devices, such as circuit breakers or fuses, to quickly trip and energize the circuit in the event of a ground fault. The NEC requires that the neutral conductor be grounded at the service entrance and other points throughout the electrical system, depending on the type of system. The grounding electrode system must also meet specific requirements outlined in the NEC. Proper grounding is crucial for ensuring the safety and reliability of the electrical system. In summary, sizing the neutral conductor for commercial load calculations requires careful consideration of several factors, including the unbalanced load, harmonic currents, voltage drop, and grounding requirements. The NEC provides detailed guidance on these topics, and it is essential to follow these guidelines to ensure a safe and compliant electrical installation. Let's revisit the key concepts. Firstly, the neutral conductor carries the unbalanced current in a three-phase system. Secondly, the NEC requires the neutral conductor to be sized for 100% of the unbalanced load, plus an additional allowance for future growth, typically resulting in 120% of the unbalanced load. Thirdly, harmonic currents, especially the third harmonic, can significantly increase the neutral current, requiring a larger neutral conductor. Fourthly, voltage drop considerations may also necessitate increasing the size of the neutral conductor. Fifthly, proper grounding of the neutral conductor is essential for safety. Now consider a more complex scenario. Suppose you are designing an electrical system for an office building with a significant amount of computer equipment and LED lighting. These types of loads are known to produce harmonic currents, which can overload the neutral conductor if it is not sized properly. In this case, you would need to carefully calculate the harmonic currents produced by these loads and increase the size of the neutral conductor accordingly. You may also need to consider using a neutral conductor that is specifically designed to handle harmonic currents, such as a K-rated cable. K-rated cables are designed to withstand the heating effects of harmonic currents without overheating. In addition to the harmonic considerations, you would also need to consider the voltage drop in the neutral conductor. The long runs of cable in an office building can result in significant voltage drop, which can cause the computer equipment and LED lighting to malfunction or operate inefficiently. To minimize voltage drop, you may need to increase the size of the neutral conductor beyond what is required for ampacity considerations alone. You may also need to consider using a voltage regulator to maintain a stable voltage level throughout the building. Finally, you would need to ensure that the neutral conductor is properly grounded to provide a low impedance path for fault current to flow back to the source. This would involve connecting the neutral conductor to a grounding electrode system that meets the requirements of the NEC. The grounding electrode system may consist of a ground rod, a metal water pipe, or a concrete encased electrode. By carefully considering all of these factors, you can design an electrical system that is safe, reliable, and efficient. Now let's discuss some practical tips for sizing the neutral conductor. When calculating the unbalanced load, it is important to consider all of the loads that are connected to the neutral conductor. This includes lighting, receptacles, and any other equipment that draws current from the neutral conductor. It is also important to consider the diversity of the loads. Diversity refers to the fact that not all of the loads will be operating at their full rated load at the same time. For example, in an office building, not all of the computers will be turned on at the same time. This diversity can be taken into account when calculating the unbalanced load, which can reduce the size of the neutral conductor required. When calculating the harmonic currents, it is important to use accurate data for the harmonic content of the loads. This data can be obtained from the equipment manufacturers or from independent testing laboratories. It is also important to consider the phase angle of the harmonic currents. The phase angle affects the way that the harmonic currents add together in the neutral conductor. When calculating the voltage drop, it is important to use accurate data for the conductor impedance. This data can be obtained from the cable manufacturers or from the NEC. It is also important to consider the length of the conductor run. The longer the conductor run, the greater the voltage drop. When selecting the grounding electrode system, it is important to choose a system that is appropriate for the soil conditions at the site. The soil resistivity affects the impedance of the grounding electrode system. In areas with high soil resistivity, it may be necessary to use multiple ground rods or a concrete encased electrode to achieve a low impedance grounding system. It is also important to ensure that the grounding electrode system is properly maintained. The grounding electrode system should be inspected regularly to ensure that it is in good condition and that it is providing a low impedance path for fault current to flow back to the source. In addition to the technical considerations, it is also important to consider the cost of the neutral conductor. The larger the neutral conductor, the more expensive it will be. Therefore, It is important to balance the cost of the neutral conductor with the performance requirements of the electrical system. In some cases, it may be possible to use a smaller neutral conductor and compensate for the voltage drop or harmonic currents by using other methods such as voltage regulators or harmonic filters. However, it is important to ensure that these methods are properly designed and installed to ensure that the electrical system is safe and reliable. In conclusion, sizing the neutral conductor for commercial load calculations is a complex task that requires careful consideration of several factors. By following the guidelines in the NEC and by using accurate data and calculations, you can design an electrical system that is safe, reliable, and efficient. Always consult with a qualified electrical engineer or electrician to ensure that your electrical system meets all applicable codes and standards. Furthermore, ongoing advancements in technology continue to influence best practices in electrical design. Smart building systems, for example, often incorporate sophisticated load monitoring capabilities. This allows for real-time adjustments to power distribution, potentially optimizing neutral conductor loading. Additionally, the increasing adoption of renewable energy sources, such as solar photovoltaic systems, can impact neutral loading, especially in systems with net metering. Therefore, staying informed about the latest industry trends and technological developments is crucial for electrical professionals. Continuous learning and professional development are essential for maintaining expertise in this ever-evolving field. Remember, electrical safety is paramount. Always prioritize safety when working with electrical systems. To energize circuits before performing any work and use appropriate personal protective equipment, or PPE. If you are not qualified to work on electrical systems, consult with a qualified electrical engineer or electrician. Hopefully, this explanation has provided a clearer understanding of neutral conductor sizing in commercial load calculations. Remember to consult the latest edition of the NEC and other relevant standards for specific requirements and guidance. By applying these principles and staying current with industry best practices, you can ensure the safe and efficient operation of electrical systems. In addition to the points mentioned earlier, consider the impact of energy-efficient lighting and appliances on neutral loading. While these technologies reduce overall energy consumption, they may also introduce harmonic currents that could affect the neutral conductor. Therefore, it is important to carefully evaluate the harmonic content of these loads and adjust the neutral conductor size accordingly. Another important consideration is the potential for future load growth. Electrical systems should be designed to accommodate future increases in load. This may involve oversizing the neutral conductor or providing additional capacity in the electrical panel. By planning for future growth, you can avoid the need for costly upgrades later on. Furthermore, consider the use of separate neutral conductors for different types of loads. This can help to reduce the harmonic currents in the neutral conductor and improve the overall performance of the electrical system. For example, you might consider using a separate neutral conductor for lighting circuits and another neutral conductor for receptacle circuits. This can help to isolate the harmonic currents produced by the lighting circuits and prevent them from affecting the receptacle circuits. Finally, remember to document all of your calculations and design decisions. This documentation will be helpful for future maintenance and upgrades. It will also be helpful in the event of an inspection or audit. By keeping thorough records, you can demonstrate that your electrical system meets all applicable codes and standards. Remember, electrical design is a complex and challenging field. It requires a thorough understanding of electrical theory, codes, and standards. By continuously learning and improving your skills, you can become a valuable asset to the electrical industry. In summary, the key takeaways are: firstly, understand the principles of balanced and unbalanced loads. Secondly, calculate the unbalanced load accurately. Thirdly, consider the impact of harmonic currents. Fourthly, account for voltage drop. Fifthly, ensure proper grounding. Sixthly, plan for future load growth. Seventhly, document all of your calculations and design decisions. By following these guidelines, you can design safe, reliable, and efficient electrical systems. One aspect often overlooked is the importance of coordination between different trades during the design and construction process. Effective communication and collaboration between architects, engineers, and contractors can prevent costly errors and delays. For example, the location of electrical panels and conduit runs should be carefully coordinated with the layout of other building systems such as HVAC and plumbing. This coordination can help to avoid conflicts and ensure that the electrical system is installed in a safe and efficient manner. Another important consideration is the selection of appropriate overcurrent protective devices. Circuit breakers and fuses should be selected to protect the neutral conductor from overload and short-circuit conditions. The overcurrent protective devices should be sized in accordance with the NEC and should be properly coordinated to ensure selective tripping. Selective tripping means that only the overcurrent protective device closest to the fault should trip, while the other overcurrent protective devices remain closed. This helps to minimize the disruption to the electrical system in the event of a fault. In addition to the technical aspects of electrical design, it is also important to consider the aesthetic aspects. Electrical equipment should be installed in a manner that is visually appealing and does not detract from the overall appearance of the building. This may involve concealing conduit runs or using decorative covers for electrical panels. By paying attention to the aesthetic details, you can create an electrical system that is both functional and visually pleasing. As technology continues to advance, new and innovative electrical products are constantly being developed. It is important to stay informed about these new products and to consider their potential applications in your electrical designs. For example, solid-state lighting, or SSL, is becoming increasingly popular due to its energy efficiency and long lifespan. However, SSL also produces harmonic currents, which could affect the neutral conductor. Therefore, it is important to carefully evaluate the harmonic content of SSL loads and adjust the neutral conductor size accordingly. Another emerging technology is Power over Ethernet, or PoE. PoE allows electrical power to be transmitted over Ethernet cables, which can simplify the installation of low-voltage devices such as security cameras and wireless access points. However, PoE also introduces new challenges for electrical design, such as the need to ensure that the Ethernet cables are properly protected from overcurrent and short-circuit conditions. By staying informed about the latest technologies and their potential implications for electrical design, you can create innovative and efficient electrical systems. Another key area to consider is the impact of electric vehicle charging on electrical systems. As electric vehicles become more prevalent, the demand for charging stations will continue to grow. This will place additional strain on electrical systems, particularly in commercial buildings and multi-unit dwellings. Therefore, it is important to plan for electric vehicle charging when designing electrical systems. This may involve oversizing the service entrance, providing additional panel capacity, and installing dedicated circuits for charging stations. It is also important to consider the load management capabilities of electric vehicle charging stations. Load management systems can help to balance the load in the electrical system and prevent overloads. These systems can also be used to prioritize charging during off-peak hours when electricity rates are lower. By incorporating electric vehicle charging into your electrical designs, you can help to support the transition to a sustainable transportation future. Remember that the role of an electrical engineer extends beyond technical expertise. It also encompasses ethical considerations and a commitment to public safety. Electrical engineers have a responsibility to design electrical systems that are safe, reliable, and efficient. They must also adhere to ethical codes of conduct and avoid conflicts of interest. By upholding these ethical standards, electrical engineers can earn the trust of their clients and the public. Also, remember, safety is always the top priority.